Hello everyone, this is Lecture 5 of ComSci 141, Equivalence of Finite Automata and Regular Expressions. In the last video, we discussed the non-deterministic finite automata, or NFA. We also discussed NFA with epsilon transitions and epsilon closure. So far, we have already seen 4 different representations of the regular language, namely the DFA, the NFA, the epsilon NFA, and regular expressions. So now, we are in the second half of our finite automata outline, and in this video, we will discuss the equivalence of finite automata and regular expressions. So we will see the equivalence of DFAs and NFAs, NFAs with epsilon NFAs, and finite automata and regular expressions. So let's start with the equivalence of DFAs and NFAs. So to show that they are equivalent, we need to show that we can turn a DFA to an equivalent NFA and an NFA to an equivalent DFA. So let's start with DFA to NFA. And this part is actually easy. So DFA is just an NFA without the non-determinism. So turning DFA to NFA that accepts the same language is easy because we only need to change one thing. So what do you think is the difference between the DFA and NFA's 5-tuple notation? The answer is everything is the same except for the transition function, delta. Okay, so in the DFA, for the transition function, we map a state and an input symbol to one state. But in the NFA, we have the transition function mapping a state and an input symbol to a set of states, which could be possibly empty. Okay, so that's the only difference. So everything else is the same, right? So the set of states for the DFA, we denote that with Q sub D, is the same with the set of states in the NFA or Q sub N. And then the set of input symbols in the DFA and the NFA are also the same. Start state are also the same. Set of final states are also the same. The only thing that is different would be our transition function. Okay, so and it's very easy to transform the DFA to NFA. So if your transition function in the DFA gives you QA is equal to P, then the corresponding transition function entry for QA in the NFA would be equal to the set containing P. Okay, so in the DFA, state Q can only transition to exactly one state, which is P. So in our equivalent NFA, the set of states that the state Q can transition to contains only one state, which is state P in this case. Okay, so it's fairly straightforward. So let's take, for example, this DFA. Okay, so the transition table of that DFA is given here. And to transform this into an NFA, we simply transform all transition function entries into sets. So from DFA, it transforms to NFA like this. So what did you notice was the change? So from one states, it became a set of states with only one state. So we only wrapped it in curly braces to denote set. But everything else remains the same, right? So that's how simple it is to convert DFA to NFA. Okay? So let's now go to the second part, which is showing that we could transform the NFA to a DFA. And this one is a little bit more challenging. Okay, so each NFA has an equivalent DFA that accepts the same language. Okay, so there is an equivalent DFA that accepts the same language, and our goal in the conversion is to remove the non-determinism to make it deterministic. Okay, so we'll remove non-determinism, and we have to make sure that the state can only transition to one state. Okay, so if we remove non-determinism, it becomes deterministic finite automata. So in converting NFA to DFA, we will use the same set of input symbols sigma. Okay, so that would be equal. However, we will need a new set of states. So we will use something called subset construction for the new set of states Q for the DFA. So we call that Q sub D, or the set of states for the DFA. And because there are new states, that means that it will also change our transition function, starting state, and accepting state. Because we cannot keep the same transition function, starting state, and accepting states because we have a new set of states. And all these three um, are dependent on the set of states Q, right? So yeah, so everything else will be changed except for the input symbols. Okay, so earlier in DFA to NFA, we only changed the transition function. But in NFA to DFA, it's only the input symbol that will remain the same and everything else will change. Okay, so um, one thing that we need to take note is that in converting NFA to DFA, the number of states in the equivalent DFA can be exponential in the number of states in the NFA. So it could grow the number of states in the equivalent DFA can grow fast, like exponentially. Okay, so let's say for example, if the NFA has 3 states, because there's exponential growth, the DFA could have up to 2 raised to 3 or 8 states. So imagine if you had, let's say, uh, 10 states, then that would mean that the equivalent DFA would have 2 raised to 10, or about 1024 states, right? So you could see the big possible explosion in terms of size, right? So, however, don't worry, because in practice, the situation isn't as bad as it looks. So we'll see later in the example that it we don't really we don't usually reach the exponential number of states. Okay, so okay, so how will we create the equivalent DFA's states? And the new set of states for the DFA, which is denoted by Q sub D, is a subset of the power set of Q sub N. Okay, and remember from the last video that the power set is just the set of subsets of Q sub N. So let's say, for example, if your Q sub N is AB, so you have 2 states, A and B, the power set will contain the empty set, okay, set containing A, set containing B, and set containing AB. So it's the set of all possible subsets of the set of states in the original NFA. Okay, so that's what we'll use as our states for the equivalent DFA. And in the equivalent DFA, the state names are denoted to look like sets of NFA states. So what does that mean? So our states in the equivalent DFA will look like this. So set A, set AB, set ABC, and so on. So this will be the names of our new state names, or new states in the DFA. Okay? But do not think of them as a set of states, but instead think of them as a state description. So the idea is, let's say if you have the state AB, that is equivalent to being to the state of being in A or in B. Okay, so if it's just state A, then you are sure that you're only in state A. If it's state AB, you're either in state A or in state B. If it's ABC, then state A or state B or state C. Because remember that in the NFA, we could be in multiple states at once. Okay, so in the equivalent DFA, we also have to model that. And the way that we'll model that is by using this state names as set of states. Okay, so for the start state, what we'll do is we'll just start with the original start state of the NFA, and then we'll wrap that in a set. Okay, so it's only this state ang start state. So there's still only one start state. So let's say if your original start state was A, our new start state in the equivalent DFA would be set of A. Okay? Now for the final states, so F sub D, it would be any state in the DFA that contains a state in the original final states in NFA. So for example, if before in the NFA, there's only one final state B, so maybe in your DFA, the final states would be something like B and AB because these are the states that contain the final state B. So there's B here, there's B here. So those are also accepted, okay, in the equivalent DFA. Because remember that we accept strings in the NFA as long as one of the paths lead to a final state. So it doesn't matter that you ended up in other states. So as long as one of the states are final states, then that is accepted. Okay? So we'll also model that in the equivalent DFA. Now for the transition function, okay, this looks like a scary equation, but really it's not. Okay, so we have our states in the DFA looking like this, right? Because they are a set of states. So P1, P2 up to Pk. So this state, given an input symbol A, where will it transition to? So the transition is the union of all from all states here in P1 up to Pk on A. So we'll take their union and use those set of states as the new state that will be the entry for this transition function. Okay, so if that doesn't really make sense, then hopefully this example makes it clearer. So for example, what is the transition function entry for ABC as a state on 0? So to do that, we'll just take the union of A on 0 in the original NFA, B on 0, and C on 0. And then since these are set of states, this one, and this one, we can just take their union, and that would be our new state that would be transitioned by this entry. Okay, so we'll see this one in an example later, but that is the equation. And the last thing that we need to take note is that we will be performing lazy DFA construction. What does this mean? So we'll only create a state if it's needed. So we don't need to enumerate all the possible exponential number of states. Okay, so only if it's reachable from the start state, then we'll add it to our DFA. Okay, so this will allow us to have the final number of states in our equivalent DFA to be less than the exponential number. Okay, so now we are ready to see an example of how to convert an NFA to an equivalent DFA. Okay, so let me here. Okay, so remember this NFA from last video, right? Wherein we had a 3x3 grid with the numbers 1 to 9, and then there's red and blue colors. So you can transition on a red, so that means that you go to an adjacent red cell. Then if it's blue, then you go to an adjacent blue cell. So this was an NFA because for example, on state 1, you can transition to two different states, let's say 2, 4. And even in 5, on red, you can go to 2, 4, 6, 8. So there's multiple possible states that you could transition to. So how will we transform this NFA to an equivalent DFA? Okay, so to start, our start state would be we have our start state here, which is 1, right? So our equivalent start state would be also 1, but in set form. Okay, so that would be our starting state. Now, to get the entry for red and blue here, what will we do? So since it's only 1 here, we'll just focus on the entry for 1 as well. So that's 2, 4, and 5. So we'll just copy that here. So that would be 2, 4, and 5. Okay? And now, since we have a new state 2, 4, we will add that here. Okay? So this is the lazy construction. So we'll just add states as they are uncovered or discovered. So 5 is also a new state, so we'll also add that in our entry. So 2, 4, and 5. So for the state 2, 4, what will be the entry for red? So if it's 2, 4, okay, we will focus on 2 and 4. So we'll get their union. So that would be 2, 4, 6, and 8, right? So that would be 2, 4, 6, 8 in total. So 2, 4, 2, 4, 6, and 8. Okay? And then for blue, we have 1, 3, 5, and 1, 5, 7. So the union of that would be 1, 3, 5, 7. 1, 3, 5, and 7. Okay? And now we have also added new states. So 2, 4, 6, 8 is not has not been added yet. So we'll add that here. So that would be 2, 4, 6, 8. And then 1, 3, 5, 7 is also a new state because it's not added here yet. So we'll also add that one here. 1, 3, 5, 7. Okay. Now let's go through 5. And since it's only a singular state, so we'll just copy whatever is the entry for 5, which is in this case 2, 4, 6, 8, and 1, 3, 7, 9. Right? So that would be 2, 4, 6, 8, and 1, 3, 7, 9. Okay, but 2, 4, 6, 8 is already an existing state here, so we don't need to add it again. But 1, 3, 7, 9 is a new state because it hasn't been added yet, so we'll add that here as well. So 1, 3, 7, 9. Okay, so let's now go to 2, 4, 6, 8 na state. So for 2, 4, 6, 8, we have to take the union of the one in the entry in 2, 4, 6, and 8. So that would be also 2, 4, 6, 8. The union of all these items is also 2, 4, 6, 8. So that would also be 2, 4, 6, 8. How about for blue? That would be 1, 3, 5, and then add 7. So 1, 3, 5, 7. And then add 9 here. So 1, 3, 5, 7, 9. So that would be our new state. 1, 3, 5, 7, 9. And notice that we don't have 1, 3, 5, 7, 9 as a state yet. So we'll also add that at the bottom here. 3, 5, 7, 9. So this is what we mean by lazy DFA construction. So just add the states as they are discovered. Okay. Now, the next one is 1, 3, 5, 7. So for 1, 3, 5, 7, we will look at 1 here, 3, 5, and 7. But their union is 2, 4, 6, and then 8. So 2, 4, 6, 8 as well. It's still 2, 4, 6, 8. So we don't need to add this one again because it's already existing here, right? And then for blue, that would be 5, 5, 1, 3, 7, 9. So 1, 3, 5, 7, 9, and then 5. So it's still 1, 3, 5, 7, 9, just like our previous entry here. Okay, so since that's already been added, we don't need to add it again. Now, let's see 1, 3, 7, 9. So we just need to remove the 5 here and instead change it to 9, right? So let's take the union of 1, 3, 7, and 9 entries. That would be 2, 4, 6, and 8. So it's still 2, 4, 6, 8 in the red. But in the blue, if we take the union 5, 5, 5, 5, 5, it's only 5. Okay, so it's only the state 5. But state 5 has already been added here earlier, right? So we don't need to add it again. And finally, we have 13579. So that would be, we'll just add this one and this one. So this is still 2468. And in the blue part, that would be 13579. Okay? And since we haven't added any new states, that's it. Okay? That's it for our equivalent DFA. Now, for the final states, we have one final state here, right? 9. Okay? So, for our equivalent DFA, we will also identify our final states. And those are the states that have a final state in the original NFA. And since only 9 is the NFA final state, let's look for states that have 9. So that would be this one, right? 1379. So we'll put an asterisk here. That's a final state. And 13579 also has a 9, which is a final state. So we'll put an asterisk there as well, indicating final state. Okay? And that's it. That's the equivalent DFA. Okay? So if we erase this one here, so you'll notice that these are more or less the same, right? So 2, 4, and 5, 2, 4, 6, 8, 1, 3, 5, 7, 1, 3, 7, 9, and so on. Yeah, so it's the same. It's the same thing. Okay? So we'll hide that for now. And let's say that we want to rename this states. So for example, if ang state 1, we'll call that A, and state 2, 4, we'll call that B, 5, we'll call that C, 2, 4, 6, 8, we'll call that D, 1, 3, 5, 7 is E, 1, 3, 7, 9 is F, and 1, 3, 5, 7, 9 is G. So since these are all of the states, if we substitute this state names, these new state names with letters for the states here, then we will get something like this. Okay, and this looks like your normal DFA transition table, right? So yeah, so we have now successfully converted our NFA earlier to the equivalent DFA. Okay, so again, the set the state names in the equivalent DFA means that they are in both of the states at the same time. So for example, 2, 4 means that you're in state 2 and in state 4. And then if it's 2, 4, 6, 8, then you're in state 2, 4, 6, or 8. Okay, so that's it for NFA to DFA. And if you'll notice, in the original NFA, we had 9 states, right? But in our equivalent DFA, we only had 7 states. Okay, so we even reduced the number of states in the equivalent DFA, when in fact we worried earlier that the equivalent DFA could have exponentially more states. And this is because of lazy DFA construction. So we didn't have to list all the possible DFA states, which could go up to 2 raised to 9, which is 512. Okay, so since we didn't list them all, then we only got 7, which are the usable states anyway. Okay, so that's it for NFA to DFA. Let's now go to the second set of equivalence, which is for NFA and epsilon NFA. And again, to show that that the two are equivalent, show that we can turn an NFA to epsilon NFA and epsilon NFA to NFA. So we have to show that it works both ways. Hindi lang siya one way. Okay? So first, let's convert the NFA to an epsilon NFA. But this one is the easy part. Why is that? Because every NFA is already an epsilon NFA. It just doesn't have any epsilon transitions. Okay? So the NFA and its equivalent epsilon NFA will have the same transition diagram. It will have the same graph representation. But will they have the same transition table? Well, they won't, because remember that epsilon NFAs need a column for epsilon. So our equivalent epsilon NFA's transition table will have an extra column for epsilon as well. So to convert your NFA to epsilon NFA, we will use the transition table to show the difference. And what we'll do is we'll simply add an extra column for epsilon, and you fill that column with null entries because there are no epsilon transitions in the original NFA. So in the equivalent epsilon NFA, there are no epsilon transitions as well. Okay, so for each row. So let's take this NFA for example. The transition table looks like this. Okay, so you have a set of states for 0, set of states for 1, possibly empty, right? To convert this to epsilon NFA, what you simply need to do is just add this extra epsilon column and fill it with null. And that's it. So from NFA, this is your epsilon NFA. So the only difference is that you have this extra column here for epsilon filled with null. And that's the only thing you need to do. Okay? So that's it. So let's now go to the more challenging conversion, which is your epsilon NFA to NFA. Okay, so each epsilon NFA has an equivalent NFA that accepts the same language. And the goal in converting epsilon NFA to NFA is to remove, of course, the epsilon transition so that we remove the epsilon part here. Because NFAs without epsilon transition, epsilon NFAs without epsilon transitions are just plainly NFAs, right? So we have to remove the epsilon transitions. And the way that we'll do this is we'll combine epsilon transitions with the next transition on a real input. So how will we do that? So in our conversion, we will keep the same set of states Q, the same input symbol sigma, and the same start state Q sub 0. But what will be different would be the transition function. So the transition function will be new in the equivalent NFA because we need to remove the epsilon transitions. Okay, so there will be changes in the transition function, and because of this, there will also be a new set of final states. Okay, so there could be additional final states because we are removing epsilon transitions. So some states that were reachable before using epsilon transitions might not be reachable anymore sa NFA. So we need to also model that in the equivalence. So we'll also have a new set of final states. So to recap, only the set of states, input symbols, and start state would be the same. The transition function and final set of states are different. Okay? So how will we change our transition function? So this is the equation that we'll use. So the transition function for the equivalent NFA, so for entry Q, state Q on input symbol A, we will get first the epsilon closure of Q. Okay, so remember epsilon closure from our previous video. It's the set of states that are reachable from that state using only epsilon transitions, right? So we'll compute the epsilon closure of the state Q first, and for all the states in this epsilon closure, we will take the delta of that state and an input symbol, and then we'll take the union of all of them. Okay, so if that doesn't make sense, we'll see this one in an example later, and hopefully it will be clear then. One last thing, for the additional final states, states that can reach a final state through epsilon transitions have to be added as final states as well. Okay, so even if these states are not final state in the original epsilon NFA, we will consider them as final states in the equivalent NFA because they can reach it through epsilon transitions. And since we're removing epsilon transitions, we have to make sure that those that could be reached through epsilon transitions before can still be final states in our equivalent NFA. Okay, so formally, the set of final states in our equivalent NFA would be all sets Q such that the epsilon closure of Q reaches a final state in the original epsilon NFA. Okay, so set of states Q such that epsilon closure contains a state in the final state. Okay, so that's what we'll do later. So now it's time to see an example of how to convert our epsilon NFA to the equivalent NFA. So for this epsilon NFA, we have the equivalent transition table here. Okay, so if this is the transition table, the first thing that we'll need to compute is the epsilon closure of each state. Okay, so let's do that now. So okay, let's do this. So for A, the epsilon closure of A is, well, it contains the state A itself, but it doesn't have any epsilon transitions, so the epsilon closure of A will only be A. Okay, now for B, okay, so for B, it will contain the state itself, which is B, but it can transition to D on an epsilon, right? So we'll also include D there. But from D, there are no more epsilon transitions, so the epsilon closure of B is only BD. Okay? Now for C, it will happen. For C, so it should contain that state itself, but it doesn't have epsilon transitions, so epsilon closure of C is only C. For D, the same thing, so start with D, but since it doesn't have epsilon transitions, then it's only D. Okay? Because remember that the epsilon closure of a state contains at the very least the state itself. Okay, how about for E? For E, we start of course with E itself, and then it could go to B and C on epsilon. So we will include B in the epsilon closure and also C. But from B, that can also reach D, so we will also include that one. From C and D, however, there are no more epsilon transitions. So these are the only four states in epsilon closure of E. That would be B, C, D, E. Okay? And then finally for F, so F will contain the state itself, F, but it doesn't have any epsilon transitions. So it will only be F as well. Okay? So these are the epsilon closures of all the states in our epsilon NFA. So this is the first thing that we need to compute when we convert epsilon NFA to NFA. So now, I've added the epsilon closures here in the as an extra entry in the table. And what we'll do is we'll now convert our epsilon NFA to the equivalent NFA. So the start state will remain the same, the set of states will remain the same, A, B, C, D, E, F. So on 0, what will happen? So what you will do is look at the epsilon closure, okay? And then get the union of all the states in the epsilon closure for that entry. Okay, so for A, it's only the state A. So we'll only look at the entries for state A, which is this one. So that would be E here and B here, right? Okay. Now for the next entry, which is on B, let's look at the epsilon closure, and that would be on B and D, right? So we have to look at entries for B and D. Okay? So for B and D, so we'll take their union. So null union null is still null. C union null is still C. Okay? So still keep that one. Now for the next one, which is C and D. So for C and D, you'll notice that they are also singletons sets. So since C lang siya and the other one is also D lang, so we'll just copy these entries as well. So there's no need to take the union since there's only one state anyway. So that will still be null and D and null and null. Okay, so that is for C and D. Now for E, this is where it gets interesting because for E, we have a lot of states in the epsilon closure. So we need to take a look at the entries for B, C, D, and E. Okay, so we have to look at all of oh, you have to look at all of this here, B, C, D, E, and same here, B, C, D, E. So we'll take their union. So the union of all of this is still just F because that's just a bunch of nulls and union with F. So it's still F, right? But the union of all of this, C, D, null, null, would be C, D. Okay, and you'll notice that this is the first new or the changed entry so far in our equivalent because previously it was null but now it became CD. Okay, and for F, since it's singleton again, so we'll just copy this one, so that would be D and null. Okay, now so that's it for the transition function. Now how about for the final states? Okay, so for our final state earlier, our final state was D. How will we know which are the final states in the equivalent NFA? So all states that could reach D in their epsilon closure will also be final states. Okay, so which states are those? So let's find states wherein D is in their epsilon closure. So D is in the epsilon closure of B. So this one is a final state. So we'll mark that here. It's a final state. D is also here in D, of course. So that is still a final state. And uh, BCDE is the epsilon closure of E. So there is a final state there. So E is also a final state. Okay, so that is how you determine the final states. For all final states, check which states have them in their epsilon closure. Okay, so this is now our equivalent NFA. So we have removed the epsilon transitions. Okay, so let's remove all of this now. So as I mentioned, the final states originally were only D, right? So if we take all states such that their epsilon closure has a final state, that would be B, D, and E, since their epsilon closures include state D. Okay, so now we can see already ang final version of the conversion. So from epsilon NFA to NFA. So this was the original epsilon NFA transition table, and now we have converted it into an NFA without the epsilon transitions. And you'll notice that only a few things have changed, right? But that's not necessarily true for all conversions. No, there could be a lot of changes in other examples, but in our example, the only entry that changed was this one, CD for E on one, and then we also added some new final states. Okay, so that's it for epsilon NFA to NFA. Okay, finally, let us discuss how the finite automata and regular expressions are equivalent. And to do this, we need to show that for every regular expression, there is a finite automaton that accepts the same language. And for every finite automaton, there is a regular expression defining its language. So they are equivalent. And again, you have to do this both ways because doing it only one way doesn't mean that they're already equivalent. Okay? So it was Stephen Kleene who invented regular expressions, and he also showed the equivalence of regular expressions and finite automaton. Um, and according to Kleene, so Kleene's theorem states that for all alphabets sigma, every regular language over sigma can be accepted by a finite automaton. So all regular languages has a equivalent finite automaton. Okay, and for every finite automaton M, the language of that finite automaton is regular. Okay, so they are indeed equivalent. Okay, so we need to show two things. Again, number one, we need to show that we can convert the regular expressions to finite automaton. And to do this, we will pick the most powerful and least restrictive type of automaton, which is the epsilon NFA, because it is the most convenient way to design. Okay, so it's easier to design using epsilon NFA because we don't have uh, a lot of restrictions. So we could do epsilon transitions, we could be non-deterministic, and that makes it easier to design. Okay. For the other side, for proving that we could have a finite that we could convert a finite automaton to a regular expression, we will pick the most restrictive type, which is the DFA, and that makes our proof easier to do. Okay, and it will use something called K paths. Okay, so there's a concept of K paths that is used to prove that finite automaton can be transformed to regular expressions. But this part won't be discussed anymore in this lecture, but just know that it is possible to transform finite automaton to regular expression. Okay, but for this lecture, we'll just focus on transforming regular expression to finite automaton. Okay, so okay, and notice here that we cherry picked the type of finite automaton that we used. So for example, for regular expression to finite automata, we use epsilon NFA, and for finite automata to regular expression, we choose DFA. So although we use those types of finite automata for our proof, um, this is only because the process is simpler using these finite automata types. But earlier, we have seen that we can convert DFA to NFA and NFA to epsilon NFA, and that all of them are equivalent. So this assures that finite automata to regular expression equivalence still applies to other finite automata types as well, even if we just use specific types of finite automata in our proof. Okay, so because if you use, for example, regular expression to epsilon NFA, but you can convert epsilon NFA to NFA anyway, and you can convert NFA to DFA as well. So in turn, you can convert a regular expression to a DFA. Okay, so let's now see um, how you can convert your regular expressions to epsilon NFAs. And to do this, we will use some basic epsilon NFA building blocks for the three operations for regular expressions, which are union, concatenation, and closure. And we will combine these building blocks to create the equivalent epsilon NFA of the regular expression. Okay, and the epsilon NFA that we will create follows a special form. It only has one start state and one final state. So it will look something like this. Okay, so only one start state here and only one final state as well. So the start state is the only state with external predecessor. Okay, so it's the only one with predecessor, and the final state is the only state with external successors as well. Okay, um, we will not allow any outside edge into the middle or into the final state. Okay, if it's an external edge for our epsilon NFA, it must pass through the start state. So the start state will guide the entrance. So you can only add an edge to the start state, but not to the middle of the NFA or to the final state itself. Okay, you cannot do that. Okay, and the other thing is no middle edges can also go outside except through the final state. So we also cannot allow a state to go outside of the NFA except through the final state. So the final state more or less guards the exit as well. Okay. Now, earlier we put quotes on the final state, because technically it could be the final state or not. What does that mean? If it's a standalone NFA, epsilon NFA, meaning it's not used as a building block, so it is really the final state or the last state. But if it's part of a bigger automaton, so if it's used as a building block, then it might not be a final state yet because it will be connected to other epsilon NFAs. Okay, so we'll see what that means in a while. So our building blocks look like this. Okay, so let me see that one here. So if it's just input symbol transition, then it's a very simple uh, transition from start to finish on that input symbol. And if it's epsilon, then that's also an epsilon transition. Okay, so pretty straightforward. Okay, if it's union, it takes this form. Okay, so you have an epsilon NFA here, E1, epsilon NFA here for E2, and this is the start and final state of E1 and E2. To get their union, okay, we'll create a new start state here and a new final state here and connect the start state to the start states of the E1 and E2 using an epsilon transition. And we'll also connect the final states of E1 and E2 to our final state using also epsilon transitions. So it will look like this. Okay, so let's see. For union, it looks like this. No, lang. So if this is um, E1, this is the start, this is the final. If this is the E2, this is the start, this is the final. We'll create a new start state here, a final state here, then we'll connect them here using epsilon, connect them here using epsilon as well, there, there, with epsilon. This is for E1 union E2. Okay, so that is for union. Now next, for concatenation, E1 concatenated with E2, we will just connect their okay, so what we'll do is, this is the epsilon NFA of E1, so this is the start state, this is the final state, and this is the epsilon NFA of E2, start state, final state. So what we'll do is we'll connect the final state of E1 to the start state of E2 using an epsilon transition. Okay, so we'll also do that. And okay, so maybe we can transfer them here. So for concatenation, so E1, E2, that would look like, so if this is E1, start, finish, E2, start and finish. So we'll connect the accepting or the final state of E1 to the start state of E2 using an epsilon transition. So this is concatenation. Okay, and then finally the last operation is closure. So if we have E star, for example, if this is the epsilon NFA of your E with the start state and the final state, here we will create a new start state and a new final state, and then we'll connect the start state to E's start state with epsilon. We'll also connect the final state of E to our final state using epsilon. And then what we'll do is we'll loop the final state of E to the start state of E with epsilon as well. So we'll get this loop back. And what this does is it allows us to use E multiple times. So, di ba, if it's epsilon star, you could do it 0 or more times. So, after you have finished, like from start, nakatapos ka na, you've reached the final state, you can go back to the start state to do it again. Okay? So, you can loop through it multiple times. Okay? But take note that we can also use 0 of E because E star is 0 or more times. So, we could create a link from start state to the final state directly using epsilon transition, and that allows us to skip E entirely. Okay, so from start, go to finish ka na agad. Okay, so this is the building block for E star or the closure. Okay, so those are the three building blocks, and we will use those three building blocks for our example here. So 0 plus 1 quantity star, then concatenate that with 1. So we will break this down into three parts. So we will take care of this first, 0 plus 1, or union of 0 and 1. So we'll call that A. Okay. And then the whole thing, star, A star, we'll call that B. Okay, so we'll use closure for that one. And then finally, A star concatenated with 1, we'll call that C. Okay, so let's start with the first one, which is union of 0 and 1. Okay, so for 0 or 1, it's pretty straightforward. So you have a 0, and earlier we saw that to create an input symbol, we just have to create a start state and a finish state, and then uh, transition on that symbol. And then for 1, that would be our 1 here. Okay, so that's 0 and 1. But then if you take their union, we have to follow this building block, right? So this is the E1 now. So we will have to add a new start state here and a new final state here, and connect the start state here with 0's start state using epsilon, start state here with 1's start state using epsilon. So we'll use epsilon here, and also connect the final states using epsilon. Okay, so that is now your um, epsilon NFA for 0 plus 1. Okay, so next, let's do A star. So we have said that this one was A earlier, so we could box this. This is the A now. Okay, so this is our A, right? If we were to use A star, we have to follow the closure building block. So remember that in closure, we need to add a new start state, a new final state, and connect the start state of the new start state with the existing start state of the expression using epsilon, and then connect the final state as well. And we also have the loop back from the A's start state to A's final state to A's start state using epsilon. Okay? Okay. Wait lang. Let me redo that one just for now. Let me change color. So I'll make this blue. Okay. So let me use blue for this one. So for A star, again, um, we'll create a new start and final state, connect them using epsilon transitions, and then loop the final state of A back to the start state of A using epsilon. And the last thing is we can add a shortcut from the start state all the way to the final state here on epsilon as well. Okay, so that is your A star. So it looks like this, right? And where A was the one that we created earlier. And then finally, we can concatenate it with 1, ang B that we created. So I'll change color again. I'll make this green for now. So, okay. So ang 1 will just have a very simple um, epsilon NFA, which is simply start and final, tapos you have the 1. And for concatenation, remember that we just have to concatenate the final state of E1 to the start state of E2. So we'll just connect this two here with an epsilon. And that's it. Okay? So, yeah, you can concatenate it with an epsilon transition to 1. So by putting it all together, this was our A that we created. This was the B that we created with the star. And then we concatenated it with C here. Okay. So all in all, it looks like this. Yeah. Let's see if we could. Yeah, it doesn't. Yeah, but that's the same thing. Okay. So you have the A here, the star, and then concatenate it with this one. So this will now be our final uh, accepting state. So this is the final start state, and this is the final accepting state here. Okay, so let's remove all those markings. And yeah, so you have your equivalent epsilon NFA. Okay, so that's it. To review, we discussed how to convert a DFA to NFA, and it's pretty simple, right? So for the transition function, you just have to change P to set P. Okay, so you just have to add curly braces. For NFA to DFA, this was the little challenging. You do this using subset construction. So you have your states for your DFA looking like set of states. So for example, state AB means that you are in the state of being in A or B. Okay, and we also used lazy DFA construction. So we only added the states as they were needed. And what we did for the transition was that if, for example, if it was on state AB, then we just took the union of the transitions on A and on B. Okay, so just took the union. For NFA to epsilon NFA, it was also pretty straightforward. We just added an extra column for epsilon on the transition function, but those are filled with nulls because there are no transition functions, and there are no epsilon transitions in the NFA anyway. For epsilon NFA to NFA, what we did was first we need to compute the epsilon closure of all states, and to get the equivalent transition function for the equivalent NFA, just take the union of all the entries for all states in the epsilon closure of that state. Okay, and then we also need to update our final states such a way that all those states that could reach a final state using their epsilon closure, those are final states as well. And then lastly we discussed regular expression to epsilon NFA. So we used the building blocks for union, concatenation, and closure, and we combined those building blocks to form the equivalent epsilon NFA. Okay, so that's it. So in summary, we have seen the four representations of regular languages, right? So DFA, NFA, epsilon NFA, and regular expressions, they all accept exactly the same set of languages, which are the regular languages. So if they are equivalent, why do we need four different regular language representations? And the reason for that is they all have their own purpose. So, for example, ang regular expression is a concise notation for regular languages. So you could write your regular language description in a mathematical manner, and you don't have to, say, draw your finite automaton to explain your regular language. Okay, so it's a concise notation. It's being used in programming languages, and behind the scenes, it has a finite automaton implementation anyway. Okay, so we can convert regular expression to finite automaton to make it work behind the scenes. Next, ang NFA, it's easier to design finite automaton since we're not restricted by determinism. So if we allow our states to transition to more than one states, then it's easier to design our finite automaton. Although the other reason for this is that it could also have exponentially fewer states than our DFA. Because if we stick with determinism, we could have a lot of states. Our finite automaton could end up with a lot of states. But if we choose NFA, it will be easier to design and will have fewer states general. Ang epsilon NFA naman allows us to connect multiple finite automata together through epsilon transitions. And you saw this earlier in the regular expression to finite automata na equivalence, right? So we used epsilon transitions to connect different building blocks. So as an example, you can also see this in keyword recognizers in compilers. So for example, if you have if you want to recognize ang else na keyword, so that would be E, L, S, and E. So that is recognized. But if you want to recognize if or else, then that would be ang if here and else na NFA. You can connect those two using epsilon transition. So it's either if or else ang mamatch niya. Okay? So, and then finally, DFA. So deterministic finite automata uses determinism, and it's very restrictive, right? Because you're only allowed to transition from one state to another state. So exactly one state. However, even if it's restrictive, DFA is necessary. Why is that? Because our computers are deterministic. There are no non-deterministic computers yet, and I'm not sure if that will be implemented in the near future. But currently, all of our computers are deterministic. So if we want to implement our finite automata, we have to use deterministic finite automata. Okay? So only the DFA can be implemented by a computer. So if you want your epsilon NFA to run, you first have to convert it to NFA and then NFA to DFA in order to run it. Okay? So everything that needs implementation has to be converted to a DFA. Okay? So that's why we have four different regular language representations. Okay, so that's it for equivalence of finite automata and regular expressions. In our next video, we will discuss finite automata extensions. So this will be next week. So we will see how a two-way finite automata works. So this time, ang finite automata can move to the left and to the right for the input symbol. And then we'll also see finite automata with outputs like Mealy and Moore machine. Okay, so that would be next week. And please take note that we have another assignment. So that would be assignment 2, which is on equivalence of finite automata and regular expressions. Okay, so that's it for this video. So I will see you next time.